Hello and welcome. My name is Alan. Grab you a chair, get you a drink. We're gonna go with another piece and ideas of opinions of Albert Einstein. Yes, I know I'm late, but let's just get into it because it's a long one. It's called On the Generalized Theory of Gravitation from Scientific American, Volume 182, Number 4, April of 1950. The editors of Scientific American have asked me to write about my recent work, which has just been published. It is a mathematical investigation concerning the foundations of field physics. Some readers may be puzzled. Didn't you learn all about the foundations of physics when we were still at school? The answer is yes or no, depending on the interpretation. We have become acquainted with the concepts and general relations that enable us to comprehend an immense range of experiences and make them accessible to mathematical treatment. In a certain sense, these concepts and relations are probably even final. This is true, for example, of the laws of light refraction, of the relations of the classical thermodynamics, as far as it is based on the concepts of pressure, volume, temperature, heat, and work, and the hypothesis of the non-existence of a perpetual motion machine. What then impels us to devise theory after theory? Why do we devise theories at all? The answer to the latter question is simply because we enjoy comprehending, i.e., reducing phenomena by the process of logic to something already known or apparently evident. New theories are, first of all, necessary when we encounter new facts which cannot be explained by existing theories. But this motivation for setting up new theories is, so to speak, trivial, imposed from without. There is another more suitable motive of no less importance. This is the striving forward unification and simplification of the premises of the theory as a whole, i.e., Mach's principle of economy interpreted as a logical principle. There exists a passion for comprehension, just as there exists a passion for music. That passion is rather common in children, but gets lost in most people later on. Without this passion, there would be neither mathematics nor natural science. Time and again, passion for understanding has led to the illusion that man is able to comprehend the objective world rationally by pure thought, without any empirical foundations. In short, by metaphysics. I believe that every true theorist is a kind of tame metaphysicist, no matter how pure a positivist he may fancy himself. The metaphysicist believes that the logically simple is also the real. The tame metaphysicist believes that not all the logically simple is embodied in experienced reality, but that the totality of all sensory experience can be uh, comprehended on the basis of conceptual system built on premises of great simplicity. The skeptic will say that this is a miracle creed, admittedly so, but it is a miracle creed which has been born out of an amazing extent by the development of science. The rise of atomism is a good example. How many Leucippus have conceived this bold idea? When water freezes and becomes ice, apparently something entirely different from water, why is it that the thawing of the ice forms something which seems indistinguishable from the original water? Leucippus is puzzled and looks for an explanation. He is then driven to the conclusion that in these transitions, the essence of the thing has not changed at all. Maybe the thing consists of immutable particles, and the change is only a change in their spatial arrangement. Could it not be that the same is true of all material objects, which emerge again and again with nearly identical uh, qualities? This idea is not entirely lost during the long hibernation of Occidental thought. 2,000 years after Leucippus, Bernoulli wonders why gas exerts pressure on the walls of a container. Should this be explained by mutual repulsion of the parts of the gas in the sense of Newtonian mechanics? This hypothesis appears absurd, for the gas pressure depends on the temperature, all other things being equal. To assume that the Newtonian forces of interaction depend on temperature is contrary to the spirit of Newtonian mechanics. Since Bernoulli is aware of the concept of atomism, he is bound to conclude that the atoms or molecules collide with the walls of the container and in doing so exert pressure. After all, one has to assume that atoms are in motion. How else can one account for the varying temperature of gases? A simple mechanical consideration shows that this pressure depends only on the kinetic energy of the particles and on their density in space. This should have led the physicists of that age to the conclusion that heat consists of random motion of the atoms. Had they taken this consideration as seriously as it deserved to be taken, the development of the theory of heat, in particular the discovery of the equivalence of heat and mechanical energy, would have been considerably facilitated. This example is meant to illustrate two things. The theoretical idea, atomism in this case, does not arise from the independent of experience, nor can it be derived from experience by a purely logical procedure. It is produced by a creative act. Once a theoretical idea has been acquired, one does well to hold fast to it until it leads to an untenable conclusion. As for my latest theoretical work, I do not feel justified in giving the detailed account of it before a wide group of readers interested in science. That should be done only with theories which have been adequately confirmed by experience. So far, it is primarily the simplicity of its premises and the intimate connection with what it is already known the laws of pure gravitational field that speak in favor of the theory of to be discussed here. It may, however, be of interest to a wide group of readers to become acquainted with the train of thought which can lead to endeavors of such an extremely speculative nature. Moreover, it will be shown that kinds of difficulties are encountered and in what sense they have been overcome. In Newtonian physics, the elementary theoretical concept on which the theoretical description of material bodies is based is the material point, or particle. Thus, matter is considered a priori to be discontinuous. This makes it necessary to consider the action of material points on one another as action at a distance. Since the latter concept seems quite contrary to everyday experience, it is only natural that the contemporaries of Newton, and indeed Newton himself, found it difficult to accept. Owing to the almost miraculous success of the Newtonian system, however, the succeeding generations of physicists became used to the idea of action at a distance. Any doubt was buried for a long time to come, but then, in the second half of the 19th century, the laws of electrodynamics became known. It turned out that these laws could not be satisfactorily incorporated into the Newtonian system. It is fascinating to muse. Would Faraday have discovered the law of electromagnetic induction if he had received a regular college education? Unencumbered by the traditional way of thinking, he felt that the introduction of the field as an independent element of reality helped him to coordinate the experimental facts. It was Maxwell who fully comprehended the significance of the field concept. He made the fundamental discovery that the laws of electrodynamics found their natural expression in the differential equations for the electric and magnetic fields. These equations implied the existence of waves whose properties corresponded to those of light as far as they were known at that time. This incorporation of optics into the theory of electromagnetism represents one of the greatest triumphs in the striving toward unification of the foundations of physics. Maxwell achieved this unification by purely theoretical arguments, long before it was corroborated by Hertz's experimental work. The new insight made it possible to dispense with the hypothesis of action at a distance, at least in the realm of electromagnetic phenomena. The intermediary field now appeared as the only carrier of electromagnetic interaction between bodies, and the field's behavior was completely determined by contiguous processes expressed by differential equations. Now a question arose. Since the field exists even in a vacuum, should one conceive of the field as a state of a carrier, or should it rather be endowed with the independent existence not reducible to anything else? In other words, is there an ether which carries the field? The ether being considered as in an undulatory state, for example, when it carries light waves. The question has a natural answer because one cannot dispense with the field concept. It is preferable not to introduce, in addition, a carrier with hypothetical properties. However, the pathfinders who first recognized the indispensability of the field concept were still too strongly imbued with the mechanistic tradition of thought to accept unhesitatingly this simple point of view. But in the course of their following decades, this view imperceptibly took hold. The introduction of the field as an elementary concept gave rise to an inconsistency of the theory as a whole. Maxwell's theory, although adequately describing the behavior of electrically charged particles in their interaction with one another, does not explain the behavior of electrical densities, i.e., it does not provide a theory of the particles themselves. They must therefore be treated as mass points on the basis of the old theory. The combination of the idea of a continuous field with that of material points discontinuous in space appears inconsistent. A consistent field theory requires continuity in all elements of the theory, not only in time but also in space and in all points of space. Hence, the material particle has no place as a fundamental concept in a field theory. Thus, even apart from the fact that gravitation is not included, Maxwell's electrodynamics cannot be considered a complete theory. Maxwell's equations for empty space remain unchanged as the spatial coordinates for and the time are subjected to a particular kind of linear transformations. The Lorentz transformations covariance with respect to Lorentz transformations. Covariance also holds, of course, for a transformation which is composed of two or more transformations. This is called the group property of Lorentz transformations. Maxwell's equations imply the Lorentz group, but the Lorentz group does not imply Maxwell's equations. The Lorentz group may indeed be defined independently of Maxwell's equations as a group of linear transformations, which leave a particular value of the velocity of light, invariant. The transformations hold for the transition of one inertial system to another, which is in uniform motion relative to the first. The most conspicuous novel property of this transformation group is that it does away with the absolute character of the concept of simultaneity of events distant from each other in space. On this account, it is to be expected that all equations of physics are covariant with respect to Lorentz's transformations, special theory of relativity. Thus, it came about that Maxwell's equations led to a heuristic principle valid far beyond the range of applicability or even validity of the equations themselves. Special relativity has this in common with Newtonian mechanics. The laws of both theories are supposed to hold only with respect to certain coordinate systems, those known as inertial systems. An inertial system is a system in a state of motion such that force-free material points within it are not accelerated with respect to the coordinate system. However, This definition is empty if there is no independent means for recognizing the absence of forces. But such a means of recognition does not exist if gravitation is considered as a field. Let A be a system uniformly accelerated with respect to an inertial system, I. Material points not accelerated with respect to I are accelerated with respect to A, the acceleration of all the points being equal to the magnitude and direction. They behave as if a gravitational field exists with respect to A, for it is a characteristic property of the gravitational field that the acceleration is independent of the particular nature of the body. There is no reason to exclude the possibility of interpreting this behavior as an effect of a true gravitational field. Principle of equivalence. This interpretation implies that A is an inertial system, even though it is accelerated with respect to another inertial system. It is essential for this argument that the introduction of independent gravitational fields is considered justified, even though no masses generating the field are defined. Therefore, to Newton, such an argument would not have appeared convincing. Thus, the concepts of inertial system, the law of inertia and the law of motion, are deprived of their concrete meaning. Not only in the classical mechanics, but also in special relativity. Moreover, following up this train of thought, it turns out that with respect to A, time cannot be measured by identical clocks. Indeed, even the immediate physical significance of coordinate differences is generally lost. In view of all these difficulties, should one not try, after all, to hold on to the concept of the inertial system, relinquishing the attempt to explain the fundamental character of the gravitational phenomena which manifest themselves in the Newtonian system as the equivalence of inert and gravitational mass? Those who trust in this comprehensibility of nature must answer, no. This is the gist of the principle of equivalence. In order to account for the equality of a inert and gravitational mass within the theory, it is necessary to admit nonlinear transformations of the four coordinates. That is, the group of Lorenz's transformations, and hence the set of the permissible coordinate systems, has to be extended. What group of coordinate transformations can be substituted for the group of Lorenz's transformations? Mathematics suggests an answer which is based on the fundamental investigations of Gauss and Riemann, namely that the appropriate substitute is the group of all continuous analytical transformations of the coordinates. Under these transformations, the only thing that remains invariant is the fact that neighboring points have nearly the same coordinates. The coordinate system expresses only the topological order of the points in space, including its four-dimensional character. The expressions the equations expressing the laws of nature must be covariant with respect to all continuous transformation of the coordinates. This is the principle of general relativity. The procedure just described overcomes a deficiency in the foundations of mechanics, which had already been noticed by Newton and which is criticized by Leibniz, and 2 centuries later by Mach. Inertia resists acceleration, but acceleration relative to what? Within the frame of classical mechanics, the only answer is inertia resists acceleration relative to space. This is a physical property of space. Space acts on objects, but objects do not act on space, which is probably the deeper meaning of Newton's assertion, spatium est absolutum. Space is absolute. But the idea disturbed some, in particular Leibniz, who did not ascribe to the independent existence of space, but considered it merely a property of things, contiguity of physical objects. Had his justified doubts won out at that time, it hardly would have been a boon to physics, but the empirical and theoretical foundations necessary to follow up his idea were not available in the 17th century. According to general relativity, the concept of space detached from the physical content does not exist. The physical reality of space is represented by a field whose components are continuous functions of 4 independent variables, the coordinates of space and time. It is just this particular kind of dependence that expresses the spatial character of physical reality. Since the theory of general relativity implies the representation of physical reality by a continuous field, the concept of particles or material points cannot play a fundamental part, nor can the concept of motion. The particle can only appear as a limited region in space in which the field strength or the energy density are particularly high. A relativistic theory has to answer 2 questions. One, what is the mathematical character of the field? 2, what equations hold for this field? Concerning the first question, from the mathematical point of view of the field is essentially characterized by the way its components transform it if a coordinate transformation is applied. Concerning the second question, the equations must determine the field to a sufficient extent while satisfying the postulates of general relativity. Whether or not the requirement can be satisfied depends upon the choice of the field type. The attempt to comprehend the correlations among the empirical data run on the basis of such a highly abstract program may at first appear almost hopeless. The procedure amounts may, or in fact, to putting the question, what most simple property can be required from the most simple object field while preserving the principle of general relativity. Viewed from the standpoint of the formal logic, the dual character of the question appears calamitous, quite apart from the vagueness of the concept simple. Moreover, from the standpoint of physics, there is nothing to warrant the assumption that the theory, which is logically simple, should also be true. Yet, every theory is speculative. When the basic concepts of theory are comparatively close to experience, e.g., the concepts of force, pressure, mass, its speculative character is not so easily discernible. If, however, a theory is such as to require the application of complicated logical processes in order to reach conclusions from uh, the premises that can be confronted with observation, everybody becomes conscious of the speculative nature of the theory. In such a case, an almost irresistible feeling of aversion arises in people who are inexperienced in epistemological analysis and who are unaware of the precarious nature of theoretical thinking in those fields with which they are familiar. On the other hand, it must be conceded that a theory has an important advantage if its basic concepts and fundamental hypotheses are close to experience, and greater confidence in such a theory is certainly justified. There is less danger of going completely astray, particularly since it takes so much less time and effort to disprove such theories by experience. Yet more and more, as the depth of our knowledge increases, we must give up this advantage in our quest for logical simplicity and uniformity in the foundations of physical theory. It has to be admitted that general relativity has gone further than previous physical theories in relinquishing closeness to experience of fundamental concepts in order to attain logical simplicity. This holds already for the theory of gravitation, and it is even more true of the new generalization, which is an attempt to comprise the properties of the total field. In the generalized theory, the procedure of deriving from the premises of the theory conclusions that can be confronted with empirical data is so difficult that so far no such result has been obtained. In favor of this theory are at this point its logical simplicity and its rigidity. Rigidity means here that the theory is either true or false, but not modifiable. The greatest inner difficulty impeding the development of the theory of relativity is the dual nature of the problem indicated by the two questions we have asked. This duality, as the reason by the development of the theory, has taken place in two steps so widely separated in time. The first of these steps, the theory of gravitation, is based on the principle of equivalence discussed above and rests on the following consideration. According to the theory of special relativity, light has a constant velocity of propagation. If a light ray in a vacuum starts from a point designated by the coordinates x1, x2, and x3 in a three-dimensional coordinate system at the time x4, it spreads as a spherical wave and reaches a neighboring point x1 plus d times x2, x2 plus d times, x1 plus d times x1, x2 plus d times x2, x3 plus d times x3 at the time x4 plus d times x4, introducing the velocity of light, c, we write in the expression the square root of dx1 squared plus dx2 squared plus dx3 squared equals c dx4. This can also be written in the form dx1 squared plus dx2 squared plus dx3 squared minus c squared dx4 squared equals 0. This expression represents an objective relation between the neighboring space-time points in four dimensions, and it holds for all inertial systems provided the coordinate transformations are restricted to those of special relativity. The relation loses this form, however, if arbitrary continuous transformations of the coordinates are admitted in accordance with the principle of general relativity. The relation then assumes the more general form sigma over mu g mu dx 4 dx k equals 0. The g mu are certain functions of the coordinates which transform into a definite way if a continuous coordinate transformation is applied. According to the principle of equivalence, these g mu functions describe in particular a kind of gravitational field, a field which can be obtained by transformation of field-free space. The g mu satisfy a particular law of transformation. Mathematically speaking, they are the components of a tensor with a property of symmetry which is preserved in all transformations. The symmetrical property is expressed as the following: g mu equals g key. The idea suggests itself. May we not ascribe objective meaning to such a symmetrical tensor as though the field cannot be obtained from empty space of special relativity by a mere coordinate transformation. Although we cannot expect that such a symmetrical tensor will describe the most general field, it may well describe the particular case of the pure gravitational field. Thus it is evident that kind of field, at least for a special case, general relativity has to postulate a symmetrical tensor field. Hence, only the second question is left. What kind of general covariant field law can be postulated for a symmetrical tensor field? The question has not been difficult to answer in our times, since the necessary mathematical conceptions were already at hand in the form of metric theory of surfaces, created a century ago by Gauss and extended by Riemann to manifolds of the arbitrary number of dimensions. The result of this purely formal investigation has been amazing in many respects. The differential equations can be postulated as field law for G mu cannot be of lower than second order, i.e., they must at least contain the second derivatives of G mu with respect to the coordinates. Assuming that no higher than second derivatives appear in field law, it is mathematically determined by the principle of general relativity. The system of equations can be written in this form. R mu equals 0. The R mu transformation in the same manner as G mu, i.e., they too form a symmetrical tensor. These differential equations completely replace the Newtonian theory of the motion of celestial bodies, provided the masses are represented as singularities of the field. In other words, they contain the law of force as well as the law of motion while eliminating inertial systems. The fact that the masses appear as singularities indicates that these masses themselves cannot be explained by symmetrical G mu fields or gravitational fields. Not even the fact that only positive gravitating masses exist can be deduced from this theory. Evidently, a complete relativistic theory must be based on a field of more complex nature, that is, a generalization of symmetrical tensor field. Before considering such a generalization, two remarks pertaining to gravitational theory are essential for the explanation to follow. The first observation is that the principle of general relativity imposes exceedingly strong restrictions on the theoretical possibilities. Without this restrictive principle, it would be practically impossible for anybody to hit on the gravitational equations, not even by using the principle of special relativity, even though one knows that the field has to be described by a symmetrical tensor. No amount of collection of facts could lead to these equations unless the principle of general relativity were used. This is the reason why all attempts to obtain a deeper knowledge of the foundations of physics seem doomed to me unless the basic concepts are in accordance with general relativity from the beginning. This situation makes it difficult to use our empirical knowledge, however comprehensive, in looking for the fundamental concepts and relations of physics, and it forces us to apply free speculation to a much greater extent than is presently assumed by most physicists. I do not see any reason to assume that the heuristic significance of the principle of general relativity is restricted to gravitation and that the rest of physics can be dealt with separately on the basis of special relativity, with the hope that later on the whole may be fitted consistently into a general relativistic scheme. I do not think that such an attitude, although historically understandable, can be objectively justified. The comparative smallness of what we know today as gravitational effects is a conclusive reason for ignoring the principle of general relativity in theoretical investigations of a fundamental character. In other words, I do not believe that it is justifiable to ask what would physics look like without gravitation. The second point we must note is that the equations of gravitation are 10 difficult equations for the 10 components of the symmetrical tensor G mu. In the case of a non-general relativistic theory, a system is ordinarily not overdetermined if the number of equations is equal to the number of unknown functions. The manifold of solutions is such that within the general solution, a certain number of functions of three variables can be chosen arbitrarily. For a general relativistic theory, this cannot be expected as a matter of course. Free choice with respect to the coordinate system implies that out of the 10 functions of a solution or components of the field, 4 can be made to assume prescribed values by a suitable choice of the coordinate system. In other words, the principle of general relativity implies that the number of functions to be determined by differential equations is not 10, but 10 minus 4 equals 6. For these 6 functions, only 6 independent differential equations may be postulated. Only 6 out of the 10 differential equations of the gravitational field ought to be independent of each other, while the remaining 4 must be connected to those 6 by means of 4 relations, identities. And indeed, there exist among the left-handed sides R mu of the 10 gravitational equations, 4 identities, Bianchi's identities, which assure their compatibility. In a case like this, when the number of field variables is equal to the number of differential equations, comparability is always assured if the equations can be obtained from a variationable principle. This is indeed the case for gravitational equations. However, the 10 differential equations cannot be entirely replaced by 6. The system of equations is indeed overdetermined, but due to the existence of the identities, it is overdetermined in such a way that its compatibility is not lost, i.e., the manifold of solutions is not critically restricted. The fact that the equations of gravitation imply the law of motion for the masses is intimately connected with this permissible overdetermination. After this preparation, it is now easy to understand the nature of the present investigation without entering into the details of its mathematics. The problem is to set up a relativistic theory for a total field. The most important clue to its solution is that there exists already the solution for the special case of the pure gravitational field. The theory we are looking for must therefore be a generalization of the theory of the gravitational field. The first question is, what is the natural generalization of the symmetrical tensor field? This question cannot be answered by itself, but only in connection with the other question. what generalization of the field is going to provide the most natural theoretical system. The answer on which the theory under discussion is based is that the symmetrical tensor field must be replaced by a non-symmetrical one. This means that the condition G mu equals G mu for the field components must be dropped. In that case, the field has 16 instead of 10 independent components. There remains the task of setting up the relativistic differential equations for a non-symmetrical tensor field. In the attempt to solve this problem, one meets with the difficulty which does not arise in the case of the symmetrical field. The principle of the general relativity does not suffice to determine completely the field equations, mainly because the transformation law of the symmetrical part of the field alone does not involve the components of the anti-symmetrical part, or vice versa. Probably this is the reason why this kind of generalization of the field has hardly ever been tried before. The combination of the two parts of the field can only be shown to be a natural procedure if the formalism of the theory only the total field plays a role and not the symmetrical and anti-symmetrical parts separately. It turned out that this equipment can indeed be satisfied in this requirement can be indeed satisfied in this natural way. But even this requirement, together with the principle of general relativity, is still not sufficient to determine uniquely the field equations. Let us remember that the system of equations must satisfy a further condition. The equations must be compatible. It has been mentioned above that this condition is satisfied if the equations can be derived from a variationable principle. This has indeed been achieved, although not in so natural a way as in the case of the symmetrical field. It has been disturbing to find that it can be achieved in two different ways. These variational principles furnished two systems of equations. Let us denote them by E1 and E2, which were different from each other, although only slightly so, each of them exhibiting specific imperfections. Consequently, even the condition of compatibility was insufficient to determine the system of equations uniquely. It was, in fact, the formal defects of the systems E1 and E2 that indicated a possible way out. There exists a third system of equations, E3, which is free of the formal defects of systems E1 and E2, which represents a combination of them, in the sense that every solution of E3 is a solution of E1 as well as E2. This suggests that E3 may be the system we have been looking for. Why not postulate E3 then as the system of equations? Such a procedure is not justified without further analysis, since the compatibility of E1 and that of E2 do not imply compatibility of the stronger system E3, where the number of equations needs the number of field components, or exceeds the number of field components by 4. An independent consideration shows that Irrespective of the question of compatibility, the stronger system E3 is the only really natural generalization of the equations of gravitation. But E3 is not a compatible system in the same sense as are the systems E1 and E2, whose compatibility is assured by a sufficient number of identities, which means that every field that satisfies the equations for a definite value of the time has a continuous extension representing a solution in four-dimensional space. The system E3, however, is not extensible in the same way. Using the language of classical mechanics, we might say in the case of the system E3, the initial condition cannot be freely chosen. What really matters is the answer to the question, is the manifold of solutions for the system E3 as extensive as must be required for a physical theory? This purely mathematical problem is as yet unsolved. The skeptic will say it may well be true that this system of equations is reasonable from a logical standpoint, but this does not prove that it corresponds to nature. You are right, dear skeptic. Experience alone can decide on truth. Yet we have achieved something if we have succeeded in formulating a meaningful and precise question. Affirmation or refutation will not be easy in spite of the abundance of known empirical facts. The derivation from the equations of conclusions which can be confronted with experience will require painstaking efforts and probably new mathematical methods. Ah, I told you that would be a long one. I am a burning up. That took a lot out of me. That wore me out. Yeah, but Einstein showing how what was known of physics at the time still depended on a lot of thought experiment. There was only so much they could do. But yeah, I'm going to go ahead and end this episode there. As always, educate thyself, think, read, study, learn. Someone tries to tell you something you have trouble believing, ask them to cite their sources. I'll see you all in the next episode. Until then, later.